Hello everyone. This is a notes for D and F block elements part 2. This notes is useful for the students of class 12 and for board examinations. Prepare the lesson well and write the examination well. I wish everybody to prepare this lesson and get good marks. Please subscribe my channel GVS Chem at 4093. Now let us discuss the inner transition elements, that is F block elements. Inner transition elements or F block elements are kept down below the main body of periodic table. F block elements have two series, that is lanthanides and actinides. Elements with atomic numbers starting from 58 to 71 are called lanthanides. They are called so as these elements start from the element lanthanum, that is lanthanum 57 atomic number. All the lanthanides have electronic configuration with 6s2 common with variable occupancy of 4f and 5d subshells with electrons. Elements with atomic numbers from 902, that is 90 to 103 are called actinides. They are so called as actinides as these elements start from the element actinum with atomic number 89. All the actinides have the electronic configuration with 7s2 common and variable occupancy of 5f and 6d subshells with electrons. Both lanthanides and actinides belong to third group. So here lanthanides starts from, of course here is lanthanum, cerium. Lanthanoid series are here lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium and lutetium. So once again, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. And actinoids start with actinum here 89, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium and lawrencium. Lanthanides belong to 6th period, whereas actinoids belong to 7th period. F block elements belong to the third shell from the outer shell. This factor accounts for some characteristic properties of these elements. Although lanthanum and actinum do not possess any F electron, it is customary to include lanthanum in lanthanoids and actinum in actinoids due to their close resemblance with lanthanides and actinoids. Now let us see the electronic configurations. Element lanthanum starts with atomic number 57. It is followed by xenon, inert gas, so 5d1 6s1, cerium 4f2 6s1, and here in all these elements the europium, gadolinium, they have half filled f orbitals, and ytterbium and lutetium they have completely filled f orbitals. So here electronic configuration, general electronic configuration of the F block elements is n-2 f1 to 14, n-1 0 to 1 ns2. Elements with fully filled, that is f14, and half filled, that is f7 orbitals are relatively stable elements, that is their reactions are very less. The extract stability of half filled orbitals is seen in the elements europium, that is 4s7 6s2, gadolinium 4f7 5d1 6s2. The element ytterbium has fully filled f orbitals with configuration 4f14 and 6s2, and extra electron in lutetium goes to 5d orbitals, that is 4f14 5d1 6s2. Thus, except lanthanum, gadolinium and lutetium, which have a single electron in 5d orbitals, the lanthanides do not have electrons in the 5d orbitals. Except this gadolinium and lutetium, remaining lanthanides do not have an electron in the 5d orbital. Now let us see the physical properties of lanthanoids. Lanthanoids are silvery white metals having low tensile strength. They have good conductors of heat and electricity. Their densities range from 6.77 to 9.74 gram per centimeter cube. The densities in general increase with increase in atomic number. Melting and boiling points of lanthanides have fairly high. However, no definite trend. Of course, in this melting and boiling points, no regular gradation or no regular change is observed from lanthanum to lutetium. Ionization enthalpies. Lanthanides have fairly low ionization enthalpies. First ionization enthalpy and second ionization enthalpy values are quite comparable to those of alkaline earth metals, particularly calcium. The first ionization enthalpies of lanthanides are around 600 kilojoule per mole and the second ionization enthalpy is about 1200 kilojoule per mole. Electropositive character. Lanthanides have a high electropositive character due to the low ionization enthalpies. Colored ions. Many of the lanthanide ions in their compounds are colored in solid state as well as in solutions. The color is due to the FF transitions. FF transition means from one F orbital to another F orbital, since they have partly filled F orbitals. Lanthanum 3 plus ion, which has F0 configuration, 4F0 configuration, and lutetium 3 plus ion with 4F14 configuration, they do not show any color due to the vacant F orbitals and fully filled 4F orbitals respectively. The magnetic behavior. The lanthanoid ions other than F0, of course in the F0 is present in the lanthanum 3 plus and cerium 4 plus, and F14 type of ions, ytterbium 2 plus and lutetium 3 plus, are paramagnetic. Except these four ions, they are paramagnetic. The paramagnetism arises due to the unpaired electrons in F orbitals. The paramagnetism rises to the maximum in neodymium, that is Nd with atomic number 60. Atomic and ionic radii and lanthanoid contraction. The atomic and ionic radii of tripositive lanthanoid ions, that is M3 plus, show a steady and gradual decrease in moving from lanthanum to lutetium. Although atomic radii decrease, do show some irregularities, but some radii decrease steadily from lanthanum to lutetium. The steady decrease in the size of the lanthanoid ions in M2 plus ion with the increase in atomic number is called lanthanoid contraction. As the atomic number increases in lanthanide series, for every portion in the nucleus, the extra electron gains to fill 4f electrons. The 4f electrons constitute inner shells and are rather ineffective in screening the nuclear charge. Thus, there is a gradual decrease in the effective nuclear charge experienced by the outer electrons. Consequently, the attraction of the nucleus for the electron in the outermost shell increases as the atomic number of lanthanide increases and the electron cloud shrinks. This results in gradual decrease in size of the lanthanides with increase in atomic number, and hence it is referred as a lanthanoid contraction. Consequences of lanthanoid contraction. Similarity of second and third transition series. The atomic radii of second row of transition elements are almost similar to those of third row of transition elements. That is, among the elements of group 3, there are normal increase in the size from scandium to yttrium to lanthanum. This is group 3, 4 and 6. Scandium with atomic radius 144 picometer, titanium 132, vanadium 122. So from scandium to vanadium, atomic radius decreases. In a 4D series, yttrium has atomic radius 180 picometer, whereas zirconium 160, niobium 146. In a 5D series, lanthanum has atomic radius 187, hafnium 159, tantalum 146. So from third series to fourth series there is increase, whereas from 4D series to 5D series the increase is very less, that is almost same. From yttrium to hafnium the increase is, the difference is only 1, instead it decreases here, whereas in sixth group from 4D series to 5D series the atomic radius is same, but after lanthanoids the atomic radii from second to third transition series do not increase as shown in the previous example. Hence, the usual increase in size on moving down the group from second to third transition elements is cancelled by the decrease in size due to the lanthanoid contraction. As a result of lanthanoid contraction, the second and third rows of transition elements resemble each other more closely than do the first and second row. Separation of lanthanoids. All the lanthanoids have quite similar properties, and due to this reason they are difficult to be separated. However, because of the lanthanoid contraction, their properties such as ability to form complexes vary slightly. This slight variation in properties is utilized in the separation of the lanthanoids by ion exchange methods. Variation in basic strengths of hydroxides. The basic strength of hydroxides decrease from lanthanum hydroxide to lutetium hydroxide. Due to the lanthanoid contraction, size of M3 plus ion decrease and there is increase in the covalent character, that is MOH bond. Oxidation states. Lanthanoids exhibit a principal oxidation state of +3. In lanthanum with atomic number 57, lanthanum 3 plus ion 4F0, that is vacant orbitals is present. Gadolinium with atomic number 64, gadolinium 3 plus ion, it has 4F7, that is a half filled F orbitals. In lutetium with atomic number 7, lutetium 3 plus ion has 4F14, that is completely filled F orbitals. Cerium, its configuration is 4F2 6S2, whereas Ce tripositive ion has 4F1, whereas tetrapositive ion has 4F0. Ce4 plus also has vacant F orbitals. Terbium with atomic number 65, configuration 4F9 6S2, that is Tb2 plus ion. Tb4 plus ion has 4F7 6S0. Tb4 plus has a half filled F orbitals. Samarium atomic number 62, configuration 4F2 4F6 6S2. Samarium 2 plus ion has 4F6 configuration. Europium with atomic number 63, configuration 4F7 6S2. Europium dipositive ion has 4F7 configuration, whereas ytterbium atomic number 70, 4F14 6S2, ytterbium 2 plus ion has configuration 4F14. Samarium, europium, ytterbium ions, their dipositive ions also exist in aqueous solutions. Although few lanthanoids exhibit oxidation states of +4 and +2, yet they have the tendency to attain +3 oxidation state Because +3 oxidation state is the most common state, +3 oxidation state is the most common state for all the lanthanoids. Example, Ce4 plus has a 4F0 configuration, Ce3 plus has 4F1 configuration. Therefore, Ce4 plus is a good oxidizing agent, that is, it takes electrons from the other substances, therefore it oxidizes other substances and itself undergoes reduction. That is Ce4 plus 2Fe plus Ce3 plus, this is Ce3 plus Fe3 plus. In the same manner, samarium has a configuration 4F6 and 6S2. Samarium dipositive ion has 4F6 configuration. Samarium tripositive ion has 4F5 configuration. Therefore, samarium 2 plus is a good reducing agent. That is, it gives its electron to other substances and reduces other substances. Therefore, it itself undergoes oxidation. So here 2Sm plus 2H2O gives 2Sm3 plus 2OH minus and H2. Similarly, europium 2 plus is also a strong oxidizing agent, while Tb4 plus is an oxidant. Chemical reactivity. The earlier members of the series are quite reactive, similar to that of calcium. With increase in atomic number, their reactivity decreases and they behave more like aluminium. Many lanthanoids react with carbon to form salts like carbides, with hydrogen to form salts like hydrates. Lanthanides react with oxygen and sulfur to form oxides of M2O3 type, sulfides of M2S3 type respectively. Cerium gives CeO2, cerium dioxide. The M2O3 oxides react with water to form insoluble hydroxides. The oxides and hydroxides are in reaction with carbon dioxide to form carbonates of type M2CO3 thrice. Oxides and hydroxides are in reaction with carbon dioxide to give carbonates of M2CO3 type. Therefore, oxide plus carbon dioxide give lanthanide carbonate. Similarly, hydroxides also. Lanthanide compounds are generally ionic. These compounds are generally colored and exhibit paramagnetism. Lanthanides occur together in nature because of their great chemical similarity and are difficult to separate. Because of the lanthanide contraction, they exhibit slight variation in their properties, and this becomes the basis of their separation by ion exchange methods. Now let us see some reactions here. Lanthanide element. All the lanthanides are represented by the common symbol Ln. Heat with carbon, they form carbides. For example, Ln3C, Lnc2, Ln2C3. They react with, they burn in oxygen and gives oxides of the type Ln2O3. They react with sulfur at high temperature and give sulfides of the form Ln2O3. When they react with nitrogen at high temperature, they form nitrides of the type LNN. They react with water to form hydroxides and hydrogen gas. They react with halogen to form halides of the type LnX3. They react with acids and hydrogen gas is liberated and respective salt is formed. So all this is about lanthanides. Now let us see actinoids. The series of elements involving the filling of 5f orbitals is called actinoid series. They follow actinium and include 14 elements from thorium to lawrencium. Actinoids are radioactive elements and they have a greater range of oxidation states. So all the actinoids are radioactive elements and their radioactivity is a very important property. Moreover, they have a shorter half-lives and therefore their accessibility for laboratory investigations is limited. The elements beyond uranium are man-made elements. So beyond uranium, that is with atomic number 90, they are artificially prepared in the laboratory by bombarding the uranium with lighter nuclei like boron, etc. So some of the physicochemical properties of actinides are discussed here. So some physicochemical properties. Oxidation states. The common oxidation state of actinides is +3. They also exhibit the oxidation states of +2, +4, +5, +6 and +7 apart from the +3 oxidation state. Thus, actinoids exhibit a greater range of oxidation states. This may be due to the fact that 5f, 6d and 7s subshells are comparable energies and the electrons in these subshells take part in the reactions. So the oxidation states are shown here. This is actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium. So here in all the actinides, neptunium and plutonium show maximum oxidation states, whereas +3 oxidation state is the common for all the actinides. So the configuration are given here. Actinium, thorium, protactinium, uranium, neptunium, they have electron in 6d subshell, and also lawrencium has a 6d electron, and berkelium has a 6d electron, lawrencium has a 6d electron. The maximum oxidation state increases from +4 in thorium to +7 in neptunium and plutonium. Actinoids form more compounds in plus 3 oxidation state than in plus 4 oxidation state. In this respect, they resemble lanthanoids. The lower oxidation states tend to be ionic while higher oxidation states are covalent. Thus, plus 2, plus 3 and plus 4 ions are hydrolyzed very easily. Physical appearance. Actinides are silvery white metals. They get tarnished when they are exposed to the attack of alkalis. Densities. All actinoids except thorium, americium have high densities. Color. Actinoid ions are generally colored. The appearance of color depends upon the number of 5f electrons. Ions having F7 and F0 and F7 configuration are colorless, and those having 2 to 6 electrons in 5f shell are colored. For example, uranium 3 plus ion is red in color. Neptunium 3 plus ion is bluish in color. Plutonium 3 plus ion is blue in color, whereas americium 3 plus ion is pink in color. Now, ionization enthalpies. Ionization enthalpies of actinoids are very low. Electropositive character. Actinoids are highly electropositive. They resemble lanthanoid series in this respect. Melting and boiling points. Actinoids have high melting and boiling points. They do not follow regular gradation of melting or boiling points with increase in atomic number. That is, there is no regular increase or regular gradation, regular change in their melting and boiling points. Magnetic behavior. Actinides are paramagnetic due to the presence of unpaired electrons. However, paramagnetic properties of actinoids are more complex than those of lanthanoids. Radioactive nature. All actinides are radioactive in nature. The earlier members have a relatively long half-life period. That is, uranium has a half-life of 4,500 million years, whereas neptunium has a half-life of 2.1 into 10 to the power 6. Neptunium has 2.1 into 10 to the power 6 years. Similarly, plutonium, americium has their half-life are in years, whereas nobelium has 58 minutes. Nobelium has 58 minutes half-life, whereas lawrencium has 4 hours half-life. Thus, the half-life of later actinides range from years to hours, that is very less. Actinoid contraction. The size of atoms are M3 plus ion decrease regularly along the actinoid series. The steady decrease in ionic radii with increase in atomic number is referred to as actinoid contraction. The actinoid contraction is greater from element to element in the series, and this is due to the poor shielding by 5f electrons. Now let us see the differences between lanthanoids and actinoids. In lanthanoids, besides common oxidation state plus 3, some lanthanoids they show plus 2 oxidation state and plus 4 oxidation state. Whereas in actinoids, besides common oxidation state of plus 3, they show higher oxidation states, that is plus 4, plus 5, plus 6, plus 7 also. Plus 2 oxidation state is quite rare in actinoids. They have smaller tendency to form complex formation, whereas actinoids have higher tendency to form complex formation. Lanthanoids, they do not form oxoions, whereas actinoids form oxoions. Some examples of oxoions are UO2 plus, PuO2 plus, UO plus, etc. Except in lanthanoids, except promethium, they are non-radioactive, whereas all the actinoids are radioactive in nature. Lanthanoid compounds are less basic, whereas actinoid compounds are more basic. Now let us see the applications of F block elements. Applications of lanthanoids. Mish metal is an alloy which contains lanthanoids. Lanthanoids are also called as rare earths. That is 94 to 95% of lanthanoids, iron 5%, and traces of sulfur, carbon, silicon, calcium, aluminum, etc. The main rare earth elements present in this mish metal is cerium up to 40%, lanthanum and molybdenum up to 44%. Mish metal is pyrophoric and is used in cigarette lighters and gas lighters, flame throwing tanks, tracer bullets and shells. All these are the uses of applications of mish metal. An alloy containing magnesium and about 3% of mish metal is used in jet engine parts. Ceric sulfate CeSO4 twice used as an oxidizing agent in volumetric analysis. Cerium salts are used in dyeing cotton and in lead accumulators and as catalyst. Lanthanum oxide is used in Crookes lenses which give protection from ultraviolet light. By absorbing this ultraviolet light, lanthanum oxide is used in Crookes lenses. Mixed oxides of lanthanides are used as a catalyst in petroleum cracking. Petroleum is a mixture of higher alkanes. These higher alkanes are subjected to cracking and they are made into lower alkanes. Many lanthanoid oxides are used as phosphors in color TV tubes. Cerium oxide is used to polish glass. So all these are the uses of lanthanoids or applications of lanthanoids. Now let us see applications of actinoids. Actinoids mostly used in as they are radioactive, they are used as fuels in nuclear reactors. Apart from thorium is used as nuclear reactor as fuel rods and in the treatment of cancer. A mixture of thorium and cerium nitrate in the ratio of 99:1 is used for making incandescent gas mantles. Uranium is used as nuclear fuel. Its salts are used in glass industry for imparting a green color, textile industry and also in medicines. Plutonium is used as a fuel for atomic reactors as well as atomic bombs. So all these are the uses of actinoids. Thank you. Students are advised to revise this lesson and prepare well for examination.